Greetings. So we are now going to talk about physical qubits. So until now qubits were just vectors in the Hilbert space or points on the Bloch sphere. But at some point they need to be actual physical tangible objects, tangible devices. And we will discuss the case of spin half systems and how these can be used to build quantum circuits. So there are many candidates for this. So you can have quantum dots, you can have cavity quantum electrodynamics, you can use superconducting quantum circuits, nitrogen vacancy centers. So there are many candidates, and there are some of the best experimentalists in the world who are working with these different, physical setups. And essentially what they are trying to do is to manipulate a spin half system. So anything which has got a spin half system, of course they can do it with some other spin states also, but this is what they try to do to implement a quantum computer. And there are three basic components of the quantum circuit. You need qubits, the quantum bits, then you need the quantum logic gates, and we have some introduction to the quantum logic gates. And if you remember, there are some fundamental logic gates in classical digital electronics, and there are similar fundamental quantum logic gates which you use in quantum circuits and quantum computers. And then at the end you have to read out, and that is a tricky part in quantum mechanics, because there is something called decoherence. So if you have a superposition state, if it interacts with anything, means you're actually setting up an experiment maybe in vacuum, and there is some tiny little bit of something and which interacts with the superposition, and any interaction can disturb the superposition. Okay, any interaction, it is like making an attempt to measure. And what does a measurement do to a superposition? The system collapses into an eigenstate. So it is not easy to sustain the superposition, and that's part of the reason as a technology, means the principles of building quantum computers are known, but physically to build them is not an easy task. There are many challenges. One of the biggest ones is the decoherence. So the readout is not all that straightforward. So you may get some errors over there. And one of the examples of a spin half system can be some ion having spin half, and then you can trap it in what is called as an ion trap. People who work in atomic physics are very familiar with these things. They know that there is this fundamental Earnshaw's theorem, which I might have used as a problem in your undergraduate electrodynamics class to show that you cannot trap an ion using static fields. Okay, you just cannot do that. And that's the Earnshaw's theorem, and you can prove it quite easily using the Gauss's divergence theorem, for example. So you need somewhat different techniques, and one of the technique is the penning trap. What you do is to add a magnetic field, or else what is called as the Paul trap, which is to use oscillatory radio frequency fields and then use the Paul trap, because you cannot do it with static fields, so you use oscillatory fields. And there are people who actually build these traps, and I like to mention the ion traps which are being built by Arvind at IIT Madras, and right here in Tirupati by our good friend Sunil. He is building an ion trap, 16-pole wire trap as it is called. And I mention these not because they are attempting to build a quantum computer, they are not. Okay, they are not in this business at all. They're doing some other kind of physics which is very exciting, which is study of ion photon collisions of some astrophysical objects and so on, photo detachment, and there are other kinds of experiments which are very exciting. But you need similar tools, similar devices. And these devices, of course, can be built. There are people who do it. And these qubits, you they should be such that they interact only weakly with environment to avoid decoherence, because decoherence is a killer, right? We just talked about it. So decoherence is a killer, you don't want it. So you need the qubits to be interacting only weakly, but at the same time you need them to interact with each other strongly, because only then you can build entanglements and multi-qubit quantum gates and quantum computers. So there are so that is the challenge in building quantum computers. So this has there are successful quantum computing machines. I will only mention some of I will give you some references so that you can read about this, and they have been there for almost 20 years now. So this is the ion trap quantum information processor. It's an article by Steen in Applied Physics, which you may read. This is more than 20 years ago. So quantum computation has come a long way, and we are going to be using the spin half qubit for our discussion in this class. And spin reminds you of pictures like this, which are absurd and they are wrong. That's not what a quantum spin is. Okay. And I discuss angular momentum algebra and spin half systems in some of my other courses on quantum mechanics, and I always tell my students that if you use any of these pictures to represent spin, 3 ghosts will come after you, which are Pauli, Dirac, and the third is me. So this has got no classical analog. When you talk about spin angular momentum, it has nothing to do with the kind of spin that Earth has about its axis or a top has. When you talk about orbital angular momentum, it has nothing to do with the kind of orbit the Earth has around the Sun. These are completely quantum properties, and they are defined best in terms of quantum mechanics, which is a set of mathematical rules on Hilbert space and operators and so on. So you have to define it in terms of the angular momentum operators, which are strange. You can take a cross product of the angular momentum operator with itself, which doesn't vanish, which is not something that any vector in classical mechanics does, right? So the commutator doesn't vanish, which is again completely counterintuitive, but that's what quantum theory is. And it is important to build your intuition so that these operators and this mathematics becomes an intrinsic part of your intuition. Okay? Then it should not appear to be counterintuitive, but actually intuitive. So we are now going to address this question of how to build quantum gates, and you have to figure out how to generate unitary transformations on the block sphere, right? So let's think of a quantum NOT gate. It is one of the simplest things to do, not the simplest quantum gate to build, but simplest quantum gate to talk about, right? So what do you have to do? You have to flip the spin. Okay, it is a two-state system, just like 0 and 1. So you have a spin up and a spin down, right? And you have to flip it. So that's the picture you see at the bottom right. Okay, and that is what you have to achieve, which is we have discussed in the previous class that you can do so by rotating it about the x-axis through pi. This is represented by the poly X gate, the poly NOT gate, right? This is also called as a bit flip gate because that's exactly what it does. And it is going to take the state 0 to 1 and 1 to 0. So that is the objective of the quantum NOT gate. And how do you manipulate the spin projection? Okay, so you have a magnetic moment, you have got the electron has got an intrinsic angular momentum which actually comes from Dirac quantum mechanics, and associated with this angular momentum there is a magnetic moment, and this magnetic moment would interact with a magnetic field. So if you write the Schrodinger equation for such a system, it will have various terms. You can have the kinetic energy term, you may have the potential energy term in the field of the nucleus, you may have the interaction term of the magnetic moment with the magnetic field. You may have different sources of magnetic moment, you may have a spin angular momentum, you may also have an orbital angular momentum, and you may therefore also have the spin orbit coupling, which is the S dot L term. So I will not be discussing the quantum mechanics of this particular coupling, which gives you to some exciting spectroscopic techniques using perturbation theory, and I will refer you to some of my earlier lectures on this, special topics in atomic physics, which are available at the NPTEL archives. You can go through that, but what we are going to focus our attention on in this class is the mu dot b term. It's the minus mu dot b term. Okay, so you have got an angular momentum associated with which there is a magnetic moment, and you are going to control this magnetic moment, the projection of this magnetic moment about the axis of quantization using magnetic fields. Okay, so this is the physical device now from vectors in the Hilbert space, points on the Bloch sphere, all right, and matrices. We are now going to talk about actual physical systems which have got magnetic moments, which will represent the qubits and how to manipulate them. So here you have a magnetic field which is a constant magnetic field along some direction. We will call this as the z direction. And the magnetic moment is proportional to the angular momentum. The proportionality involves what is called as a Bohr magneton. So I have defined the Bohr magneton over here, and some of these details you will find in the earlier lectures, or of course you will get it from just about any book on elementary quantum mechanics or atomic physics. And our focus is going to be on the spin angular momentum, so which can be written in terms of the Pauli vector operator, okay, which is the same as the spin angular momentum operator, except that it is scaled by this factor h cross over 2 to define the spin. Okay. So our focus is on this interaction term minus mu dot b. Mu is minus mu b times 2s over h cross, all right. S itself is h cross over 2 times the Pauli sigma operator, and therefore you can write this in terms of the Pauli operator, but mind you, the Pauli operator is a 2 by 2 matrix operator. So these are matrix vector operators. They are represented by matrices. So the algebra that you will do will make use of matrix algebra. These are vector operators, and therefore the algebra you will do will make use of vector algebra and vector calculus. And these are quantum mechanical operators. So whatever properties quantum operators require, in particular their commutation rules or non-commutation rules and so on, so all that will have to be taken into account. So quantum properties, matrix properties, vector properties, all of this mathematical machinery is going to be employed together to proceed with this analysis. So this is your time dependent Schrodinger equation. Its solution will tell you how the system evolves with time. It is the rate at which the quantum state is changing with time, okay? And we know what the NOT gate does. This is the poly NOT gate. This is the spin flip gate, as we know. We have discussed this in the previous class. And I have now extracted the time dependence of the stationary state, which is e to the minus iet over h cross, or minus I omega t. So that is the dynamic phase. So any physical state evolves with time if it is a stationary state. Its phase is going to change. And I have now extracted the phases e to the minus iet, but there are two states. One is the state spin half up and spin half down. So they correspond to E0 and E1. Okay? So E0 represents one state and E1 represents the other state. So that is the reason you have these two different phases here, and I can extract one of these, I can factor it out, and then I am left with this. So there is no phase factor with this, right? But this one has got the difference E1 minus E0. Okay, this one has the E1 minus E0 factor. The common factor which is extracted out, I can forget about it because it is a general overall phase, and we are already doing qubits on this block sphere. We have reduced the two complex numbers having 4 real numbers to only 2 real numbers by factoring out, by dispensing one overall phase factor, and this e to the minus I E0 t which we have extracted can be buried into it, right? So we forget about it. The other one has got a dynamic factor which is E1 minus E0 in units of h cross. When you divide it by h cross, you will get the circular frequency omega. Okay, E divided by h cross will give you the circular frequency omega. And you have the difference E1 minus E0. So what is this difference coming from? This difference is coming because you have subjected a spin system to a magnetic field. So in the absence of this magnetic field, the two states, the spin up and the spin down, they had the same energy. But now the spin up and spin down will interact differently, and this difference is because of this interaction which serves as a perturbation. And this perturbation is going to lift the degeneracy. So there is a certain symmetry which existed before you applied this perturbation. That symmetry is now broken by the perturbation, and the degeneracy is lifted. And there are now two energy levels. One is E0, the other is E1. And this difference you can get from first order perturbation theory in quantum mechanics, which again we have discussed in other classes. But I will take the result now. And the physics students amongst you will know this result very well. The first order perturbation correction is nothing but the matrix element of the perturbation operator in the unperturbed states. Okay, that is the first order perturbation correction. So this is your interaction operator. These are your unperturbed states, N, L, ML, MS, right? And you take this matrix element, and it is very easy to see that this will be proportional to the magnetic field. other than the Bohr magneton, which is just the measure of proportionality. So one level, whatever be its energy before you apply the magnetic field, one of the two states will get an energy which is above this and the other less than this, and the difference between them will be twice this amount. Okay? So that is what you have got. So delta E, which is plus or minus the Bohr magneton times B0, and this common energy, which is degenerate state, this degeneracy is lifted and you have a spin up and a spin down, which corresponds to the state 0 and 1, and they now have different energies E0 and E1, which are the ones which are coming here. Okay? So this energy difference in units of h cross is a circular frequency omega, which is called as the Larmor frequency. So this is the Larmor frequency. It is EB0 divided by m times c. Okay? And if you now want to flip, the up has to go down and down to up. Then you need a magnetic field which is strong enough and invert this. Now you need fairly strong magnetic fields to do that, which is really not very practical. But it is much easier to do that if you apply a transverse oscillatory field, a radio frequency field. Okay. So you have a magnetic field which will lift the degeneracy so that the spin up and the spin down have different energies. The energy difference is twice this perturbation correction, and in units of h cross it will give you the Larmor frequency. So you apply a transverse field. So this is what you have on the application of a constant magnetic field, and you have the angular momentum to be precessing about the z axis, about the direction of the magnetic field. Now this is a cartoon. You have to remember that this object is a quantum object, and it is coming simply from the fact that the spin projections along x and y cannot be measured simultaneously. So they are not compatible. Okay? So there is a quantum uncertainty between them, which is represented by this commutator jx comma jy equal to I h cross jz, and this is the algebra, the commutation algebra, which governs the dynamics. But this is a good representation. It is a useful representation of using this precision. Okay? And this precision is taking place at the Larmor frequency, which is EB0 by m times c, right? And what is going to happen is, notice this phase factor now, EIB0 by mct. Where is this coming from? This is coming from the Larmor frequency. Okay, we got it on the previous slide. The quantum qubit is this, and as time passes, it will evolve such that the phase phi over here will go to phi plus EB0 by mct. Okay? So this is the dynamic evolution of the state. Okay? It is the same qubit, superposition of spin up and spin down. The coefficients are cosine theta by 2 and sine theta by 2, but the sine theta by 2 has got the second real number which you require, which is e to the I phi. But then there is also this magnetic field which you have now switched on, as a result of which the dynamic phase will evolve, and that is built into this relation now. So, the degeneracy is lifted and the solution to the Schrodinger equation will be given by what I have written here along with this time dependent phase. And what we will now do is to apply a transverse field. Okay, so the main field that we applied first is like this, and now we apply a transverse field which is oscillatory, whose electric vector will oscillate from one end to the other along one particular axis. So, it will be polarized along one axis, which we can say is the x axis. It will have an amplitude which I call as B perpendicular, okay, which is different from B0, and then it is an oscillatory field represented by a cosine function which goes from 0 to +1, then to 0, and then again to -1, and then to 0, and so on. So, it will have the sinusoidal or cosinusoidal, if you like, oscillations. So, that is the oscillatory field that we apply. So, the picture of the oscillatory field, so you have got an oscillatory field which is polarized along the x axis, which is represented by this black arrow. It goes from one end to the other, like the cosine function from +1 to -1, right. But I can break it into two rotating fields of half the amplitude rotating in opposite directions, one clockwise and the other anti-clockwise. So, if you look at these circles which are actually on top of each other, the red represents the rotating field which is counterclockwise, and the blue represents clockwise. So, both are of half the amplitude as you need for the black arrows, okay. So, that what will happen is that their vertical components will cancel and the horizontal components will add up, and they will give you the polarized oscillatory field along the x axis. So, effectively you have resolved this linearly polarized field in two rotating fields, one clockwise and the other anti-clockwise, but of half the amplitude. So, that is the half that you see in this equation, right. So, the clockwise and the counterclockwise each has half the amplitude as the B perpendicular, and now the spin which was originally subjected to B0 is now also subjected to a field which is orthogonal to that, and that is going to change this angle theta, okay. So, this angle which you had at which this vector, this cartoon vector was precessing, okay, that angle will now change because of this perpendicular field, and you can change that angle, you can change it. So, if it was this, you change it further and further and further and further and further till it flips, and you have a quantum NOT gate. Got it? So, that is the idea. So, using the static steady constant magnetic field, you resolve the degeneracy, okay, and then apply a transverse oscillatory field which will flip the spin up to spin down and spin down to spin up. So, that is how you can get a quantum NOT gate using electron spin. So, the result is a quantum NOT gate, and it is going to flip at a certain frequency which is called as a Rabi frequency, okay. So, the theta will change to theta plus a certain angle, which will be the angular frequency multiplied by the time over which you apply this oscillatory field. And now you can control it, because how long do you want to apply it? You want to apply it as long as is required till theta changes to theta plus pi, right. So, you can apply this. You notice that theta is changing at the Rabi frequency, which is denoted by omega r. So, there are two omegas now that we are talking about. One is the Rabi frequency and the other is the Larmor frequency, okay, and they have different magnitudes altogether. So, this is the picture that we have got, and you want to look at the time evolution. So, theta is now changing because of this transverse field. It will change at this rate given by the Rabi frequency, depending on how much time you have subjected the system to this oscillatory field. So, the theta changes to theta plus omega r times t, and you have the corresponding change in the sinusoidal term as well, and this phase we had already seen changes to e to the b0 mct through the Larmor frequency because of the application of the steady constant magnetic field, and that impacts the dynamical evolution of the quantum state, right. So, you have two frequencies, the Larmor frequency and the Rabi frequency. So, keep track of the omegas, which one is which, all right. So, you have got the time evolution. So, you start with time t equal to 0 when you have the quantum bit, the manner in which we described them as points on the block sphere, but that quantum bit will now evolve with time because of these two simultaneous interactions. One is the interaction with a steady magnetic field, which makes the angular momentum precise, and the other which is an orthogonal oscillatory field, which will change the angle at which this precision takes place, and you can control this, okay. So, the Rabi frequency is usually in the it is of the magnitude of kilohertz, but this one is in gigahertz. So, there are very different orders of magnitude, okay. So, you have the time evolution of this quantum bit, which involves this precision angle to change because of this Rabi field, which is an orthogonal field, and then the phase phi changes due to the dynamic evolution of the state, because you have got an applied magnetic field, you have lifted the perturbation, you have applied a perturbation, lifted the degeneracy, and now you have got this phase, dynamical phase e to the I EB0 by MC times t, okay. And you have these two frequencies, the Larmor frequency and the Rabi frequency. And if you now apply this orthogonal field for a certain amount of time tau, such that this angle omega times tau is exactly equal to pi, you will achieve the flip, okay, because theta is changing to theta plus omega t. So, if omega t is equal to pi, and that t which will make omega t equal to pi is what I call as tau. So, you have to apply that field for as much time, and now you have a control. Okay. So, using these controls you can actually implement quantum gates. So, now you get an idea of what quantum gates are and how they can be physically implemented. The idea is simple. The actual implementation is a huge challenge, and that requires the kind of investment which Google and IBM can do, all right. So, this is what gives you the quantum NOT gate, and then of course, we talked about operations on just a single qubit, But what makes the quantum computer so powerful is the entanglement between several qubits. All right, so you really need a multi-qubit quantum gate. So we have discussed single qubit quantum gates so far, and we will now get into multi-qubit quantum gates, which means that you had a cat which was dead or alive and a superposition state, and you have another one which is also in a state of superposition of being dead and alive. All right? And then we are going to discuss the possibility of entanglement between these two cats which are both dead and alive. Okay? So this is the 2-qubit system that we will now begin to discuss. So you are going to talk about entangled 2-qubit systems. So you have got one qubit represented by one Bloch sphere, the second qubit represented by another one, all right? And then there is some entanglement between these two qubits that we are going to discuss. So both are identical spin half systems. Okay? So now a 2-qubit state will now be represented by this tensor product of the two single qubit states. So this is like a direct product of two vectors. You have used direct product of vectors when you did coupling of angular momentum. When you couple J1 with J2, then you get direct product vectors of those vectors which belong to the Hilbert space of angular momentum 1 and angular momentum 2, right? So it's something like that. So you have this direct product or tensor product of single qubit states. So now you have 0, 0, 0, 1, 1, 0 and 1, 1, right? There will be 4 coefficients, alpha 0, 0, alpha 0, 1, alpha 1, 0, alpha 1, 1. Each would be a complex number having 2 real numbers, right? But then you will still be able to subject it to the same kind of analysis that you will use orthogonality, normalization. So some of these real numbers will be redundant. So if you sum the squares of the complex matrix, coefficients, then it is normalized to unity. So what is the probability of finding the first qubit in state 0? It will be the sum of these two probabilities, because both have got the first qubit to be 0, even if the second qubit is different. Okay? So you can determine the relative probabilities using this. Now if you carry out a measurement which returns the first qubit in the state 0, then the 2-qubit vector will be given by this superposition, because it will still have the possibility of the second qubit being in either state 0 or in state 1, and this whole state will be normalized. So you have to divide it by the sum of the squares of the complex coefficients, right? So now let us take this 2-qubit state and we ask this question: can we write this 2-qubit state as a tensor product of two single qubit states? Is it possible? It may be possible, it may not be possible. There is no reason to assume that it always will be possible, not unless you check it out, right? So as a matter of fact, it is not possible when the two qubits are entangled. Okay, that is what entanglement is about. You cannot write this 2-qubit state which has these 4 terms as a product, as a direct product of two single qubit states. That is possible if and only if these are not entangled. And there is this entanglement which is really necessary for quantum computation. Okay? So, in general this is not possible, and for entangled states it is not possible. For those which are not entangled, you can do that, and you will see why the statement is holds. So, the result is that when you have entangled multi-qubit systems, you cannot factor them into tensor products of lower qubits. So, let us take an example. Let us take two single qubits. Let us take a particular example in which we give some values to the coefficients A0 and A1. Okay? You can quickly check out that the states that we have used are actually normalized. Sum of the squares add up to unity, right? 1 over 2 plus 1 over 2 is equal to 1 even in quantum mechanics, right? Sum of the squares of 3 over 5 plus 4 over 5 also add up to 1. So, these are properly normalized single qubit states, right? And now you construct the direct product, the tensor product of these two vectors. So, now you multiply them out, okay. So, what do you get? You get 3/5 times 1 over root 2 times 0 0, then you get minus 3/5 times 1 over root 2 times 0 1, and you get the other two terms. Get it? Right? So, we have just multiplied out the two. So, let us carry out this multiplication, and now we write the two qubit systems not as ket of one multiplying the ket of the other, but a ket representing the two qubits. So, we use only one ket symbol, right. So, that is the 0 0, 0 1 for the next, 1 0 for the third, and 1 1 for the last. And you have got the coefficients there. You can quickly check that the coefficients now are different from what we had earlier, but if you take the sum of the squares of all these four coefficients, they again add up to 1, which is very easy to see, right, and you have a properly normalized two qubit system. Conversely, if you were to start with this, you would expect that this is a state which you can factor. That it is factorizable is no wonder, because we started with two separate single qubits. And now I am going to take advantage of the fact that we now start with a two qubit state which we know is factorizable. Okay? So, that will lead us to identifying when such a factorization cannot take place, which will give us the description of entangled qubits. So, this state that we have built can actually be factored. So, let us begin our argument at this point, that this is a factorizable state. And then I am going to argue that if you have a state which I have now written as a superposition of 0 0 and 1 1 with equal coefficients 1 over root 2, and I am going to argue that this is a two qubit system which cannot be factored like this. Okay? This is the point I made earlier, that it is not something that you can take for granted, not without checking. So, I have now given you a two qubit state which is a superposition of 0 0 and 1 1, and I claim that when that this state cannot be factored. It is in fact what is called as a Bell state or an entangled state. So, in other words, we have to prove that this state cannot be written as a superposition of alpha 0 plus beta 1 as one factor, and the second factor is gamma 0 plus delta 1. If we could write this, there are two brackets over here, this is one qubit, this is the other single qubit, and the product of such two single qubits cannot generate what I have written as the Bell state. Okay, let us prove it. So, under what condition would the right hand side lead you to the left hand side? So, let us examine the right hand side, which is alpha 0 plus beta 1, which is one qubit, multiplying the second qubit, which is gamma 0 plus delta 1. Let us multiply them out. What do you get? Alpha gamma 0 0, do it slowly, alpha delta 0 1, then beta gamma 1 0 and beta delta 1 1, got it, right? So, this is what you get from the direct product, okay? And we need to ask if this direct product can be equal to what we have claimed to be the Bell state. Now, if the left hand side is equal to the right hand side, then alpha delta must be 0, which is the coefficient of 0 1, because it does not appear on the right hand side. These are all linearly independent vectors, right? And beta gamma should also be 0. And if for alpha delta to be 0, either alpha has to be 0 or delta has to be 0 or both have to be 0. And if beta gamma has to be 0, either beta has to be 0 or gamma has to be 0 or both have to be 0. Now, if alpha is 0, then the coefficient of 0 0 vanishes, alright, and if delta is 0, the coefficient of 1 1 vanishes. You do not make much progress, right, okay, and if both are 0, it is time to go home, right. So, the conclusion is that there are these two qubit states which cannot be factored. These are called as Bell states or entangled states. Entangled states cannot be factored as products of single qubit states. So, classical computer cannot simulate a quantum computer, which also means that it cannot simulate nature, because nature is quantum mechanical. Okay? And this was the famous remark which Feynman made, and you have to read it in his own words. Nature isn't classical, damn it, and if you want to make a simulation of nature, you would better make it quantum mechanical, and by golly, it's a wonderful problem because it doesn't look so easy. This is what Feynman said in 1982, all right. This was in a keynote address he gave at MIT at a conference on physics of computation. This is what triggered the interest and excitement about quantum computation, other than the work of Deutsch, which also I will be talking about in the next class. So, entanglement is an important aspect of this. Classical computers will not achieve this, and a quantum computer will make use of these entangled states, the Bell states, and that is something which a classical computer will never be able to do. The classical computer which you are making from the binary digits will never be able to do what a quantum computer does. So, quantum computer with n qubits can be in 2 to the power n different states simultaneously. Okay? Now, what an amazing achievement this is. You know, an exponential function is awesome. All right, it grows very rapidly. Okay, you ask for exponentially increasing grains of rice on a chessboard, which is this famous story which I am sure you have all heard, right? So the exponential function, the power of information that the quantum computer can process is enormous. So the Bell states are those which are maximally entangled, they are maximally correlated. These are 2-qubit states. You also have multi-qubit entangled states, but we will not get into those. The 2-qubit Bell states are hard enough, so let us stay with them for a while. All right? And there are 4 of these Bell states. We used 1. Okay? And if you do the same kind of analysis for the remaining 2, for the remaining 3 actually, you will be led to the same conclusion that they cannot be factored. I will leave it as an exercise. Okay? So there are 4 Bell states represented by phi plus and minus and psi plus and minus. Okay? These are different superpositions, as you can see, 0 0 1 1 and 0 1 1 0. And you consider a measurement of the first bit of phi plus. Okay? And you will get 0, right? What is the probability of getting this result? It is the square of 1 over root 2. So the probability is half, 0.5. Okay? The probability of getting 1 is also the same. So it is random. Okay? But then if you carry out this measurement and then ask what is the probability of getting 0 or 1 for the second qubit, that is something that you can guarantee because of the entanglement. There is no ambiguity left there. Okay? A measurement on 1 qubit will give you complete information about the second qubit because of the entanglement. Okay? And this is what you can do with entangled qubits, the Bell states, which you cannot factor as products of single qubit states. So I will stop here for this class and we will continue from this point in the next. If there is any question, we can take it.